So today we are going to talk about the computer performance, and here are the topics in today's discussion. We start from the very short description of all these words. I believe that many of you already get used to all the terms here. So, for example, the embedded computers. In the last 10 years, there are lots of advancement in computer technologies. So nowadays we can see lots of embedded computers. Anyone ever use the Raspberry Pi?
I used it before.
Okay, some of you, right? I will show you what else that you can use. Let me go to the browser. I will show you what else that you can use. Lots of system nowadays. Some of you might ever use Jetson before. This is what I think that is really nice. For example, the NVIDIA Jetson Nano Developer Kit. This one is really good. I used this 2 years ago, and I used it 2 years ago, and for the image processing. And do you know how many processor core of this embedded system? Let you guess. What? How many cores in of the CPU in your computer? My computer has 8 cores. How about yours? 4,
I also have 8 cores.
8, 16?
Me too. I have 8 cores.
Okay. And what do you think? How about this one? The Jetson Nano, its size is you can hold it in your palm. Can you guess the number of CPU core of this processor? Let's guess.
So I think
60.
16? More than that. Any numbers?
60.
60? More than 60.
Oh, wow.
What else? Who else can come up with the number? It has 128 core for this embedded system. And you may guess that, oh, this is really nice. And lots of cores, meaning that it is very powerful. And you can see here, it used the power as little as only 5 watts. Very nice. This is the trend of the current of the processor. And let's look at some more example. Here is another one. Pi64 is the 64-bit embedded system. And here is the example. This one is a bit bigger than the Jetson Nano, but it gives you many choices. For example, you can use the development board like that, or you can use it as the card like this. When you use it as the card like this, you can let's see some more example. you can notice that here is the board and there are lots of slots here. You can put the CPU card into these slots, so you can make the cluster of embedded computers by using the board like this. You can see that the embedded system here is very advanced nowadays, and it's quite cheap. Can you guess how much for this board, the development board like this? And don't forget that the processor is 64-bit. Can you guess how much it is? Any idea? Or it's too early to ask question? No one want to answer. Can you guess?
Can you ask it again? I just go to the toilet.
Yeah, can you guess how much for the board like this? This is a 64-bit processor, and it looks like Raspberry Pi. It can run Ubuntu, and you can see that there are lots of input-output interfaces, and there is what is this one is HDMI port, and here is the LAN port, and there are 2 USB ports. Can you guess how much it is?
Is that 1,000?
1,000 baht or dollars?
Baht.
Oh, it's very close. This one is $29. It's very cheap. This one is only $29, and you can see that here is the interface for the data port. You can put the Wi-Fi data port here, so this one can use the Wi-Fi connection, including Bluetooth, and the Wi-Fi data port here is just only $19. It's quite cheap. And this is the example of embedded computers. So now we go next to other terms. I think I don't have to explain the personal mobile devices here. Everyone use it. I think that everyone has the mobile devices. For example, your phone. Now the smartphone is, I think it's for everyone. And desktop computing. Everyone use the desktop computing, including the high-end, low-end laptops. And how about the server here? What do you think about the server? What's the difference between the server and the desktop computer? Any idea?
I think the desktop computer is for running an application, and the server is to hold the server.
To hold the server? Can you have the definition of the server that you just mentioned?
It's like a node in the internet that manage the connection with a lot of computer.
All right. Okay. Let's see something like this. If you have a laptop, is this a server?
No.
Okay. One more question. If I have a laptop and I install the database server into my laptop, is my laptop a server now?
Well, if you open that application, then it will become a server. Yes,
All right. So the server is the hardware or the software?
the software.
All right. Yeah, I would like to let everyone think about the server in terms of software, because if you have a software, you install it into any machine, that machine become a server. So the server itself should means the software that should mean the software that you are using, not the hardware itself. But the term of the server here, what does it mean? Here, the term of the server here means that it is this special hardware that allow you to scale it easily and have more reliability, and it may have some redundancy. That is the server in this meaning, because when you think about the farm observer, you're talking about the scalability. When you talk about the let's say if I have the failure of the power supply, I have the secondary power supply to supply the power to my machine. So in that case, I mean the redundancy. So here, when we talk about the server in terms of hardware, we talk about how can it scale up, or is that possible to have the redundant part? That is the server in this sense. It's not about the software that we just discussed previously. How about the next? Supercomputers. What do you think the difference between server and the supercomputers? Any idea? It's really quiet today.
I would say that the supercomputer is hardware, right? The hardware that is designed to do a lot of calculation.
Yeah, excellent. That is one of the good definition of the supercomputers. And you can see the example of the supercomputers here. Here is the cluster of computers. A cluster of computers mean that you put a lot of computer hardware and make them connect to each other by using the computer network. And you need special software that can manage all the nodes in the network, so that when you submit the job into the cluster, many computers can parallelly work or do that job simultaneously. That is the example of a supercomputer. All right, and next you may hear some terms here. For example, the terms organization and the architecture. There are some differences between the two terms here, computer organization and the computer architecture. When we talk about the computer organization, usually we mean the CPU, the buses, the memory, and most of them here are in the hardware side. But when we talk about the computer architecture, usually we discuss about the instruction set architecture. Instruction set architecture nowadays, the domination one is the x86. Many of us use Intel or AMD x86 or ISA64. This is one of the most versatile instruction set in the world. And 20 years ago, you may hear about the PowerPC, but I think that the PowerPC already outdated before some of you were born. And here is the software side. In our course, we are going to definitely I think that you know the high level programming language. For example, you may study C, Python, or Java before, right? Which language you learn in previously?
There's a Golang and Python.
Oh, Golang and Python. That is really nice. And how about here? Do you have any problem understanding this code?
No, I can understand it.
Okay, you understand it, right? So here is the example of the high level programming language. And in the very next chapter, we are going to learn how we change from the language like this to something like this. And here we call the assembly language. But this course is not about the assembly programming language. So we are going to learn it just only one chapter, and then we move on to something else. And some courses, long time ago, we taught students how to do something like this for the whole course. But nowadays, understanding this kind of language is not that very important now. But anyway, you have to understand the language here because understanding all the syntax or how we implement the assembly language can help you to understand how the computer works. And after discuss about the assembly language, next we are going to make ourselves as the assembler. The assembler can translate the assembly language into the machine language, and this is the machine language. And by the end of chapter 2, you will be able to do something like this by yourself. Is that very challenging? Thinking about this, I know that most of you can just do the high-level language like this. This program is quite easy for you. Next, we are going to write a program in assembly language like this. And then we are going to translate the assembly language into the machine language like this. So by the end of chapter 2, finally you can do this. That is what I hope. And here is the big picture of the computer organization. On the right hand side here, we have input and output. And then we have the processor. So in chapter 3, we are going to discuss about the processor. Actually, we first in chapter 3, we are going to discuss about the data representation in computer, for example, the number system. And then we are going to see how the processor process the fundamental algorithms, for example, the adding, the multiplying. And next, you can see that we have the a control system, and we have the data path that connect everything in the processor. So all of this we are going to discuss in chapter 4. Here is the basic components in computers. Anyone never disassembly your machine? If you've never done something like this before, you may try by yourself. I have a machine like this, and but this is not a picture of my machine. But let's have a look what inside the computer. Here is the hard drive, and here is the processor. You can see the cooling system here. That is a cooling system, and that is also the cooling system as well. And here is DVD drive, but nowadays is obsoleted. And here is the memory slot. Anyone of you ever assemble the PC by yourself?
I used to do it.
Oh, excellent. You know, when I was this student, I worked at the PC shop, and at the time I assembled about 10 PC a day, and I got paid pretty nice, about $100 a day. That is not very bad. What do you think? Next, we are going to discuss about the computer performance. Here is the growth of the processor performance. You can see that in the very early day, about 40 years ago, the computer, the speed of the computer is only about, the speed of the development is only about 25% per year. And here is a very, the growth rate of the computer is very high. It's about 52% per year. It means that if you buy a computer today, and the next year there will be a computer that faster than that 50% faster than the computer today. But nowadays, it's not that very fast. The growth is not that very fast now. Nowadays, the growth rate is just only about 22%. So it means that if you buy a computer today, next year we expect to have a 1.2% faster computer. As you may notice in the previous slide that, let me go back to this slide. As you may notice in this slide that you can see the frequency of the processor. The frequency of the processor is about 2.8 gigahertz, 2.9, 3 gigahertz, 3.5, 3.6, and 3.8. You may notice that the frequency is not go up very high. It's not the same pace as here. You can see this one is 500 megahertz, 600, 1.3, 3 gigahertz. But here, the frequency is it's just like we hit the limitation of the frequency now. Why we have something like that? Look at this slide. Here we just zoom in, and we can notice that the frequency of the processor is almost stable around this point. 2 gigahertz, 3.6, 3.4 gigahertz, something like that. This is because we hit the power constraint. If we put more, if we have the higher frequency, the hotter the processor will be. And when it is very hot, it consumes a lot of power, and it cannot work very well. And this is the power constraint of the processor, and that is why we have the processor frequency just only this. But how can we have more performance computer if we cannot increase the frequency? We will discuss about this in the very next slide. But here, look at this picture. I believe that some of you may ever seen the picture like this before. This is a computer, and the same computer here. And this is the very first electric computer. It's about 70 years ago, and it made from vacuum tube. And if we use the performance per unit cost as the reference, for example, this machine, if you have the performance per unit cost as 1, and we can compare with the current technology, which is much better than this one, because here is in 2013, and you can notice that about 9 years ago, the relative performance per unit cost is about 250,000 million times better than the vacuum tube technology. And look at this slide. This is the computer performance from Apple Mac M1 8-core GPU, and we get this number. What do you think about this number? Does it mean anything to you? It's nothing much, right? Because you don't know what does it mean. You can see the number is 21,000 something, and it should be correct. But if you see something like this, we have 21,000 here for the M1 CPU, but we have 40,000 here for M1 Pro, and we have 71,000 here for M1 Max. Oh, when you see many numbers here, you notice that, oh, this machine, this processor should be much better than this one. What I would like to infer is that when you see the number of any benchmark, if you see the number alone like this, you don't know what it means. But if you have the comparison between the processor, for example, in this slide, you see the number here, you can see the number here and there, so you can compare them. The same as the very previous slide. When you see the number here itself, you don't know what it means. But if you see the different numbers here, you can compare them and you notice that, oh, this machine is much better than that one. What I am trying to say is that the computer performance is something about the comparison. The number itself, it does not tell you much. But if you have the comparison, for example, this is another example. And here is from Intel. You can see, let's have a look at this one. Intel Core i9 is 44% better than the baseline here. The Intel Core i9 here is better than the baseline here is 10% better than the baseline. Again, here the Core i9 is 14% better than the baseline, and here is 9% better. In this slide, what can you notice from the picture here? In terms of computer performance?
Like the processor from Intel Core i9 it's quite very fast than like other processor.
Yeah. Anything else? Thank you for that point of view.
This picture also shows that the newest generation of Intel run faster than the old gen.
Yeah.
At maximum like Adobe up to 44%.
Right. Thank you very much. Anything else? Look here. Here is the Adobe Creative Cloud. The processor is about 44% better than the baseline if you use this program. And if you use the AutoCAD, it's only 14% better. But if you use the Revit, it's only 9% better. It does tell you that the performance of one processor is not better than the other processors in the same number for all applications. In this application, it's 44% better, but here it's just only 9% better. So it depends on the application that you are using, not only the hardware itself. So the computer performance depends on not only the hardware, but also the software. And here is the very summary, the very brief of how to make the computer fast. You can use the faster devices. For example, you can use the higher frequency CPU, or you can use the better circuits, or you can use the much more modern computer organization or architecture. For example, instead of using the 16-bit, you can use a 32-bit processor, or you can use the 64-bit processor. When we talk about the 64-bit processor, and we believe that 64-bit processor should be faster than 32-bit processor. Do you have any question in mind? Something like this. Why not 128? Why not 256-bit processor? If the number of bits can make the processor faster, why not we have the bigger one, like 128 or 256 bit processor? Any idea? $10 ago,
Well, I guess, I think like 128 or 256 is too much for the computer to process. So it's just like we use 64-bit is enough.
Oh, all right. Thank you for your comment. We will discuss about the size of the data when we discuss about the processor in chapter 3. In chapter 3, we are going to look at the adder. I believe that you know the adder before. You can use the something like Lipo adder, and we will analyze the performance of the Ripple adder when the number of bits is higher. For example, from 16 to 32 bits, we will see something we call gate delay. It means the time that we spend from when the circuit get the input and how long it can produce the correct output. That is the gate delay. And in chapter 3, we will discuss about the gate delay of the adder, and we will see that the longer or the bigger of the data, the longer the gate delay of Ripple adder is. That is why we cannot nowadays in the technology nowadays, we believe that 64 bits is a good choice. We cannot we can go to 128, but it is not necessary for now. So I will discuss again about the gate delay in chapter 3. And next, we can use the parallel circuits. For example, we have more CPU cores. That is how can we make the computer faster. Next, I would like you to spend about 5 minutes to visit the top500.org and have a look by yourself, and then we will come back and discuss what is in there. Let's try. You can do it by yourself, or you can look what I'm going to I can open it now. Let's say top500.org. This is the website, and here I would like you to see the list. You go to the list menu and top 500 and look at the November 2021. This is the latest list. Have a look on the list here. For example, we have supercomputer Fukaku, you have Summit, and so on. And look at the number of cores. And here is the teraflops and the power it uses. You go through this website for a few minutes and then we'll come back and discuss on the information that in this website. So what did you find on the information on this website? I would like you to discuss all together here.
Mostly news regarding supercomputer.
Yeah. What else? What is the processor that they are using? For example, the Fukaku, this is the processor, A64FX. This is the processor. And the Summit here is used the IBM Power 9. This is the processor. And you can see the third one here. It also uses IBM Power 9. That is from the States. But from China, look at the supercomputer from China here. This one, the processor is Sunray SW here. So they're using different processor than what we are using on the desktop. And what else that we can summarize from this information? You can see the number of cores. The number one supercomputer has 7 million cores, more than 7 million cores. But you can look at the number 4 here. The number 4 here, it has more than 10 million cores, CPU cores. So the number of cores may not able to tell you which one is faster. And what else? Look at the this column. This column is Armax, and the unit here is teraflops, T-flops per second. What does it mean? T-flops per second. You know that a tera is 10 to the power of 12, and here is the floating point operation. It means that 1 teraflop is 1 trillion floating point operation per second. And here is the row number 1 is 442,000 teraflops. Is very good. And what else that you can notice from the information here? Which country have the most supercomputer in the list?
USA, I think.
I think so. The world number 2, the world number 3, number 5, number 6, and number 10. And who else? Japan and China also has this very good supercomputers. Here is China has China is on number 4 and number 7. And 3 or 4 years ago, Tianhe is the world number 1, but nowadays is number 7. So I think many countries developing supercomputers. All right, and I believe that you should come back to this site from time to time to look at the update of the top 500 supercomputers, and hopefully one of them will be in Thailand very soon. 10 years ago, I visited the biotech. Biotech is the center, research center in Thailand, and they have a very good supercomputer. At the time, 10 years ago, the supercomputer I used, it had 256 gigabytes of RAM. Oh, that was very superb. But nowadays, 256 gigabyte of RAM, you can easily find it on the market. It's quite, it's look like the commodity now. For example, the machine that I'm using on the back of my desk, it has 128 gigabyte of RAM. So, but I cannot say that it is the supercomputer. It's just the normal desktop computer. Okay, let's go back to the slide. From the data that we just saw in the top 500, and here is the caption that I captured from is a picture that I captured from that website. I have the question here. How can we judge the performance of the computer? Can we use the clock speed in terms of megahertz or in terms of gigahertz? Or can we use the number of memory? Or we use the MIPS? MIPS means million instructions per second. Or can we use the teraflops? Teraflops is here. Tera of floating point operations per second. What do you think? How can we measure the performance of the computer? Can we use any of these
by
numbers? Yeah.
by measuring how fast or the time it can compute, calculate, or execute.
Yeah.
Because at the final, the specs is just help us to compute faster, and at last we still look at the time, how fast it is.
Yeah, definitely. That is a very, very good answer. Yeah. In general answer, the time that the computer spend on the program that we want it to execute is the good measure that we want. If the machine can use the shorter time, means that it has better performance. If you use longer time to process the job, it means it has less performance. That is the general for the question like that. But in the computer center, the time that the processor processes one job may not be a big issue, but instead the throughput or the amount of work that can be done in a given time, for example, in the 1 second, how many jobs can be done? That is the throughput that computer center may concern. But in our course, we are considering the first term here, the time that computer use to execute the job. But in the very last chapter that we are going to discuss in this course, we are going to discuss about the CPU scheduler. And at the time, you will know that the time that computer used to execute a job means that we have CPU time. This is the time that CPU spend on the job, and the queuing time. Because most of the computer have to process many jobs, and if there are many jobs in the queue, some jobs may have to wait, and most of the time spent on the execution time will be on this part. But for simplicity, in the very beginning here, we are considering only on the CPU time here. So this part, we omit this part. Or we can say that the execution time here, just only the CPU time, not the queuing time. But I just would like you to know that in real life, this time is not that very short. But for simplicity, we just assume that this one is 0. And here is the very fundamental formula to calculate the performance of the computer. The performance is equal to 1 over the execution time. And we can compare the performance of machine X over the performance of machine Y. And we can say that X is n times better than Y if the performance of X divided by the performance of Y equal to n. Or just use the time to execute a job. We can use the time of machine Y to execute the job divided by the execution time of the machine X equal to n. These are the very simple formula to calculate the computer performance. And because we assume that the queuing time is 0, so the execution time, we can assume that it is equal to the CPU time. And CPU time is the number of clock cycles that CPU use to execute the job times the CPU clock cycle time. So this is number of cycles and times the cycle times, so we get the total time. Or we can simply use the CPU clock cycle times, CPU clock cycles divided by the clock rate. Let's look at this example here. If we have two computers, computer A and computer B, computer A has the CPU time for one program to run one program for 10 seconds, and computer A has the clock rate equal to 10 gigahertz. Computer B run the same program, but it takes only 6 seconds to finish the job. but we don't know the clock rate of the computer bay. Assume that we know that the computer bay take 1.2 times as many clocks as the computer A. How can we find the clock rate of the computer B? This is quite simple. For computer A, we can calculate the clock cycles of computer A, and clock cycle of computer A is just like this. It's from the simple formula that we just discussed in the last slide. So we know the CPU clock cycle of computer A, and from the equation, we say that CPU clock cycle of computer B is just 1.2 times that of computer A. So we can calculate the CPU clock cycles of computer B just like this. And then we can just substitute this number into our formula. And finally, we get the clock rate of the computer B is equal to 2 GHz. Any question of this example?
No.
There are some more formula for the computer performance calculation. Look at the term here. We have the CPU clock cycle. We can calculate it as the instruction count times the clock cycle per instruction, or simply CPI. When we substitute this equation into the previous formula, we can get this one. IC times CPI times clock cycle time, or IC times CPI and divided by the clock rate. Here is the example how to use that kind of formula. Let's say, look at the table here. There are 3 instruction classes, class A, class B, class C. What does it mean, instruction classes? You may notice that we have different type of instruction. For example, if I say something, I write down something like this. If I have the integer x, and then let x equal to 10 plus 1, something like this. This is a very simple instruction. But if I have instruction like integer of the array y, let's say have 10 of them, and if I calculate something and put it into y0, let's say I put x into y0, this kind of instruction is a bit different than this kind of instruction. And how about this one? If, let's say, if true, then calculate something like this, x equal to 1. The instruction like this, it's different from this one as well. So here is the example of different classes of instruction classes. Maybe this is class A, maybe this one is class B, and here is class C. We will discuss about instruction classes in chapter 2. But first, let's say that we have 3 classes of instruction, and each class has a different CPI. class A, let's say that it has only has CPI equal to 1, and B has CPI equal to 2, and class C has CPI equal to 3. It means that in class A, it uses only one clock cycle to complete the instruction. But in class B, the processor has to take 2 clock cycles to finish to complete the instruction in class B. And likewise, the processor have to use up to 3 clock cycles to finish the instruction in class C. And the information in the table here, we have code number 1 and code number 2. As you may know that if we would like to write a program, if you write a program and another person also write the same program that can do the same thing, you yourself and the other guy can have different numbers of instructions. Let's say you write code number 1 and the other guy write the code number 2. In code number 1 has only 200 of the instruction in class A and 100 class B instructions and 200 class C instructions. So in code 2 have the different numbers of instruction here, 400, 100, and 100 in class A, B, and C respectively. The question is, which code execute the most instruction? This kind of question is very simple. It's just add all the numbers here. So in code number 1, it has 200 of class A, 100 of class B, and 200 of class C instructions. So in total is 500. How about code number 2? It has 400 of class A, 100 of class B, and another 100 of class C. So in total 600 of instructions. So you can answer the first question here. So code number 2 execute more instruction. And how about the second question? Which one is better? Which one is faster? Code number 1 or code number 2? When we have the question about the faster, we have to calculate the time. This time means faster. So next, we look at the time. But to calculate the time, we need the clock rate or we need the clock cycle time. But we don't have both. We don't have this, we don't have that. We don't have the clock cycle time, we don't have the clock rate. So we cannot calculate the time by directly. But we know that the CPU time is equal to the number of clock cycle times the clock cycle time. So we don't know this one, but we know that both code 1 and code number 2 run on the same machine, so the time is the same. So we can compare the number of clock cycles. If if we have more cycles, meaning more times. Okay. Now we go to the solution here. the CPU clock cycle of code number 1 is like this. You can see the number of class A instruction is 200 times the CPI of class A plus the number of class B instructions times the CPI of class B. And here is the number of class C instruction times the CPI of class C. And from the solution here, we can see that code number 1 takes 1,000 cycles, while code number 2 takes only 900 cycles. So code number 2 is faster. And the last question asks about the average CPI. So average CPI can calculate by using the clock cycles, number of CPU clock cycles divided by the number of instruction. So here is 1,000 over 500, and we got number 2 here for code number 1. And CPI for code number 2 is 900 over 600, which is 1.5. In this table, you can see that we have algorithm here, we have a programming language here, we have compiler here, we have we can see the instruction set architecture here. This table gives us the idea of what the hardware and software components affect the performance of the computer. When you study about the data structure, you know that the algorithms are very important. So, and when you study about the programming language, you may notice that some language, for example, C programming language is usually is faster than Java. And the compiler, I'm not quite sure whether you ever heard about the optimized compiler or not. Most of the compiler, you use it for free, right? You can use, you can download the Java compiler, you can download the Go interpreter, you can install the Python, and all of them are free. And they are very good. You can write the code and you can compile them, and you can deploy whatever you compile to the computer system. And it can run very nice. But the terms optimized compiler here, if you search, if you use a search engine to search for the optimized compiler, you may find some of the optimized compiler. If you want to use it, you have to buy, and it is very expensive because it can reduce the instruction count. When you reduce the instruction count in your program, what does it mean? We reduce the CPU time to process the job, because CPU time is IC times CPI and then divided by clock rate. if you can reduce the number of instructions that you use in the program, means that we have less CPU time to spend on. So your program will run faster. And how about the instruction set architecture? If you use the better instruction set architecture, it can affect the clock rate, it can affect the CPI, and definitely the instruction count. You may use the less instruction count, you may use the higher clock rate, and you can have the better CPI. We are going to discuss about all of this in the next chapter. But any question before we go to the next slide? Okay, we are going to look at the new topic here. Previously, we discussed about the computer performance, and we can compare one computer to the other. Now, let's say if we have one computer and we would like to improve that computer. So let's say in this case, we have two classes of instruction, class A and class B. Class A means the class that we want to improve. But class B is the instruction class that we don't want to touch it. So we leave it untouched or unchanged at all. If a program spend F%, maybe this one should be percent or ratio to execute the class A instruction. So the rest of the time the program is on class B. Or maybe this one you can use the percent as well. We can calculate the speed up of the whole system from the improvement of class A. Let's say if we have the improvement of class A by factor P, let's say that P is greater than 1. For example, if the class A is 20% better than the previous version, meaning that P is 1.2. And the question is, if we improve class A by 20%, what is the overall performance of the system? And this is how we apply the MDALOR to answer this kind of question. So in the next slide is the summary of the formula that we use to calculate the speed up. The speed up means that if we have the time of the old system, so this number is should be larger than this one, and here is the CPU time of the new system. So when we divide them together, we get this speed up, or we can calculate it from the performance of the new system divided by the performance of the old system, like this. But the thing is, how can we calculate the CPU time of the new system if we know only the factor of the improvement and the percentage of of class A? Let's look at the third formula here. Don't forget that F is a fraction of the improved part. For example, class A is F%. And P is the improvement factor, P, and we know that P is greater than 1. So here is the time of part A, and here is the time of part B. Because part B is untouched, we don't change anything in class B, so the time of class B should be the same. And part B is only 1 minus f% of the whole of total. It remains the same, right? But part A, we improve part A by p%. That is why we divide part A by p here. And for the whole, from the total here, we get the CPU time of the new system. So when we use the CPU time of the old system divided by the CPU time of the new system, we can get the speed up like this. So here is the same formula. It's nothing new. Because if you use the CPU time of the old system there and put and substitute this equation into the above one, you will get this. You can try by yourself. Okay. And how about the maximum speed up here? This is the maximum speed up here. You can notice that it's a bit different from the above equation here. How can we get the maximum speed up? This one is quite easy too, right? Because if we want to make it maximum, what does it mean? It means that we don't have part A anymore. We have only part B. So we cross part A out. So the new CPU time of the new system has only the time that we spend on part B, which is 1 minus f times CPU time of the old system. And we just substitute this part into the above equation. Finally, we get this one. And this is the Amdahl's law. Let's see the example here. How can we use the Amdahl law to calculate this speed up? Let's look at the information that in this slide. If you have the memory operations for 30% of all execution time, what does it mean? It means that for 100%, the memory operation is 30%. This is a memory, and 70% remain untouched. It's the same. And we have a new widget called Cache, and it speeds up 80% of the memory operations by the factor of 4. What does it mean, the 80% of the memory operation? We can calculate for 80% of the memory operation here. So in total is 30% times 80%. And here is equal to 24%. And 24% of the memory of the 20% here, it's speed up by the factor of 4. What does it mean? 20% of the time here is faster 4 times. It's 4 times faster. So means that 24 divided by 4, we have only 6%. So instead of 20% here, we have only 6% there. And how about the next information here? The second new widget called L2 Catch speed up half of the remaining 20% by the factor of 2. This is the remaining 20%. So half of this. So 30% times 20% is 6%. So over here is 6%. And half of it means that only 3% that we are talking about in L2 Catch. And L2 Catch can be speed up by a factor of 2, in that we divide this by 2. This one is only 1.5. So this one is at only 1.5. And here is the same. So in total, the time that we use for the execution is this part remain untouched. This part from 20% it reduced to 6%. This part 3% is remained as it is. And how about this part 3%? It reduced by the factor of 2, so we have only 1.5 here. So we add all this number all together, and we get the number like this. 80.5%. So the speed up is just only 1 over 0.805, and here is the speed up. So in total, speed up is about 24%. This is how can we use the $M to see the improvement of when we improve some part of the computer system. Any question of this example? Okay, great. And this is the last content of the first chapter, and the rest is about the fallacy. The fallacy means something that you believe, but it might not true. It might not be true. For example, here, the fallacy number 1. The computer at low utilization uses little power. This is our belief. If we use it only a little, the power should be little, but it is not that. It's not that true. Look at the column here. This is 100% load. It used the power 269 watt, but with 50% load, it used 227 watt. So the difference of the power here and there is only a little, but the load here 100% and there is 50%. And when you look at the 10% power, 10% of load, the power is 174. You can notice that from 100% to 50%, 50% power is 84% of the 100% load. So the load reduced from 100 to 50, but the power that the machine used dropped from 100 to only 84, not 50. And again, this number also confirms that our belief is not that true. You see that the load is just only 10%, so the power it consumes should be a very similar number, should be 10% or a little bit more. But here you can see this is 65%. And you have to know that this is just only for the server, not for the notebook or tablet. It's for the server only, because in the server, most of the time we think about the performance. So most of the time we let the processor to run in full speed. That is why it uses a lot of power. That is policy number 1. But if you're using laptop, definitely laptop is the number is better than this number in the table here. If you're using laptops can the processor itself can reduce the speed, so it would use less power. The next policy, policy number 2. Long time ago, we used this number, MIPS, million instruction per second, to give the user the idea of how fast the machine is. But nowadays, we don't use this number anymore. Why we don't use this number anymore? Let's have a look at this example. Here is how we calculate MIPS. MIPS is the number of instruction count divided by the execution time times 6 to the power of 6, because we want to change from to the number of million. And from our discussion previously, we know that execution time we can substitute that terms by using this instruction count times CPI and divided by clock rate, or we can get MIPS equal to this term, the clock rate divided by a CPI times 6 times 10 to the power of 6. Look at the table here. We have computer A and computer B. The question is, which machine has the higher MIPS? We have the instruction count here. For machine A is 10 billion, for machine B is 8 billion. Clock rate for the machine A is 4 GHz, the same as machine B, but the CPI of machine A is 1, but the CPI of machine B is 1.1. To calculate the MIPS, we just substitute the number from the table into the equation here. Okay, MIPS for machine A equal to clock rate 4 GHz divided by CPI of machine A, which is 1, and then times 10 to the power of 6. How about MIPS of machine B? Four GHz divided by 1.1 times 10 to the power of 6. From the number here, this is divided by 1, but this one is divided by 1.1. So the divider here, the denominator here is greater. So this number is less than the MIPS of computer A. So we can say that MIPS of computer A is higher. How about the time for machine A and the machine B? Which machine is faster? To calculate the time, we can calculate by using the formula here: instruction count times CPI divided by clock rate. So time for machine A, instruction count is 10 billion times CPI, which is 1, divided by clock rate, which is 4. How about CPU time for machine B? Is 8 billion times CPI, which is 1.1, and then divided by the clock rate as well, 4. Machine A is 10 billion divided by 4 gig, but for machine B is 8.8 billion divided by 4 gig. You see that the denominator is the same, but the numerator here is 8.8 is less than the denominator here. So the time for machine B is less than the time for machine A, meaning that machine A is faster. So here is the example that we cannot use MIPS as the metric to tell which machine is faster. Any question from this example? Okay, and that is all. Before we go to the break, let's look at the assignment. And here is the assignment that I would like you to do it, and it deals on this Friday. We have the assumption here. If you are planning to buy a new computer, I would like you to go to all the websites and grab some information about the computer specification, and you choose the components that you want to use and give the reason why you choose such component, and try to discuss about the following topics. Are you going to use laptop, or are you going to buy desktop, or you prefer tablets or whatever, or you prefer the server specification? It's up to you. And try to look at the performance of, let's say, CPU that you choose, or you can look at the performance of the RAM or the cache, and maybe you can discuss about the price. You choose that components because it's lower price, or you can think about the performance per cost. Performance per cost is better, even the price is higher, but the performance per cost is much better, so you prefer that components, for example. And you can discuss about you prefer this machine because you use this kind of applications a lot. For example, you take lots of time in gaming, so you prefer the gaming laptops, for example. And you may want to have the desktop with the GPU because you use a lot of graphic applications. Try to discuss all these things all together, and you can write it in a document file or PDF. You can put some text, some images, graphs, or any reference that you might find out on the internet. And some of you already give me your ID and name that you want to present the result. And It's just because we have many students in our class, so the presentation should be very short, about 3 to 5 minutes presentation on next Monday. That is the first assignment. And don't worry if you are not in the list of the presentation next week. We are going to have presentation like this along the way. So if you are not in the list, don't worry. Any question before we taking a break? Okay, we are going to have 15-minute break, and then we will come back to the lab session. How about this? Let me come back at around 11 o'clock so that we can have quite a long break today. Okay, see you at 11 o'clock.